So today we're diving deep into language models, specifically how they handle massive amounts of information, like, entire code bases or huge scientific
Oh,
papers.
yeah. That's a challenge for sure. But there's this new technique called natively trainable sparse attention, or NSA for short, that's really changing things up.
NSA. Okay, so how does this NSA actually work?
Well, it addresses a fundamental limitation in current language models. You see, standard detention mechanisms, they're powerful, but they become computationally very expensive, especially as the text length grows. It's a real bottleneck.
Yeah, I see. It's like trying to run a complex simulation on an old computer. The hardware just can't handle it.
Exactly. And that's where NSA comes in. It's sparse. Instead of paying attention to every single word in a text, it focuses only on the most important parts.
So it's like a detective scanning a crime scene. They don't analyze every inch. They just focus on the key evidence.
That's a great analogy. That's exactly how it works.
But how does it know which parts are actually important?
Well, it's a two-pronged approach. First, NSA is designed to work really well with modern hardware, so it can leverage things like parallel processing to speed things up.
Oh, so it's taking advantage of all the horsepower we have available now.
Exactly. And second, and this is the really crucial part, it's training aware, meaning it learns to be sparse during the training process itself.
So it's not just a passive observer. It's shaping its own attention.
Exactly. It's like a student learning to prioritize information while studying.
That's really cool. But can you walk me through how this actually plays out in practice?
Absolutely. So NSA has three main components. The first one is token compression. Imagine you're reading a research paper. You might highlight the key sentences, right?
Right.
That's essentially what NSA does. It compresses those blocks of text into smaller, more manageable chunks. And that captures the core information.
It's like creating a summary.
Precisely. But it doesn't stop there. It also does token selection. This is where it gets even more selective. Within those compressed chunks, it pinpoints individual tokens that are super important. It's like highlighting specific phrases within those key sentences you've already marked.
Gotcha. So it's just compressing. It's also choosing the right details.
Exactly. And then the third component is a sliding window mechanism. This helps NSA maintain context by focusing on the most recent information. Think of it like reading a novel. You keep the last few pages in mind as you go right.
Oh, yeah.
That's essentially what the sliding window does for NSA.
So we have compression, selection, and then the sliding window for context.
Exactly.
Now, you mentioned earlier that NSA is hardware aware. Can you expand on that a little bit?
Sure. One of the really cool things about NSA is that it can leverage parallel processing, especially on GPUs. GPUs are designed to handle massive amounts of data all at the same time. And NSA's approach really aligns well with this. By processing those blocks of text in parallel, it speeds up both the training and the inference.
So it's not just about the algorithm itself. It's about how it works with the hardware.
Exactly. And that's one of the reasons why NSA is so promising.
Yeah, that makes a lot of sense. So it sounds like we've got the mechanics down, but does NSA actually deliver? Does it live up to the hype?
Well, that's what we're going to be exploring next, and I think you'll be impressed. They've tested it on a variety of tasks, everything from general language understanding to really complex reasoning tasks. And it consistently outperforms those standard attention mechanisms.
Okay, I'm definitely intrigued. Let's dive into those results and see what NSA can really do.
So before we dive into those results, I think it's worth looking at some of the things they tried that didn't really work. It shows just how clever this NSA approach actually is.
Oh, yeah. I love a good detective story.
Yeah.
So what were some of those dead ends?
One early idea was clustering similar tokens together in memory. They thought by grouping related information, you could make the attention process much more efficient.
Yeah, that makes sense. Kind of like organizing your bookshelf by genre.
Exactly. But it turned out to be way more complicated than they thought. Like the clustering algorithms themselves, they added a lot of computational overhead, so it kind of negated the efficiency gains.
So it was like taking one step forward and two steps back?
Yeah, pretty much. And there were other problems too. They ran into trouble with these systems that use a mixture of experts architecture. Basically, these models, they divide a task into smaller subtasks. And each subtask is handled by a specialized expert.
So it's like having a team of specialists instead of just one generalist.
Exactly. But when they tried clustering in this context, it created imbalances. Like some experts ended up with way more information to process than others.
Oh, so like one member of your team is drowning in work, while the others are sitting around with nothing to do.
Exactly. Not very efficient. And on top of that, there were just practical challenges. Like they needed to recluster things periodically. And the training process had to be done in a very specific order. It just wasn't practical.
So clustering was a no-go. What else did they try?
Well, they also looked at different ways to calculate these block importance scores that NSA uses. Those scores help determine which blocks of text are worth focusing on.
Right, right. It's like a map that highlights the spots where the treasure is buried.
Exactly.
So how did they go about calculating those scores?
Some of the approaches used neural networks to learn the scores, but there's a problem there. The selection process itself, it's not something that a neural network can easily learn directly, so they had to add this thing called an auxiliary loss.
So it's like adding another layer of complexity.
Yeah, exactly. And often it made the training process less stable, and it didn't necessarily even improve the model's performance.
Another dead end.
Yeah. They also experimented with some simpler methods that didn't involve learning any parameters. These were easier to implement, but they often missed important blocks. It's like using a metal detector that's only sensitive to gold. You might find some treasure, but you'll miss a lot of other valuable stuff.
Right, so you're trading off simplicity for accuracy.
Exactly. They even tried a hybrid approach, like starting with standard attention, and then switching to this simpler block-wise selection later in the training, kind of like easing the model into this sparse attention world.
That's an interesting idea, but I'm guessing it didn't quite work out either.
Nope. None of those methods could really match the performance of NSA. And this brings us back to those visualizations we were talking about earlier. Remember how they showed that attention patterns tend to cluster together?
Yeah, like words that are near each other often have a similar level of importance. It makes sense, but it's cool to actually see it.
Exactly. And that was really key to the development of NSA. It kind of validated this idea that selecting and processing those blocks of text together could be a really effective strategy.
So it wasn't just about throwing away information. It was about understanding how language is structured and how attention actually works in practice.
Exactly. And this is where NSA really shines. It's not just about being sparse. It's about being smart about what to focus on.
Yeah, that's a really good point. Okay, so we've talked about what didn't work. Now let's talk about what did. You said NSA consistently outperformed standard attention. Can you give me some examples? What kinds of tasks are we talking about?
Well, they tested NSA on a bunch of different tasks, from basic language understanding to really complex reasoning. They used these standard benchmarks to measure things like question answering, text summarization, even code generation.
Oh, so pretty comprehensive.
Yeah. And the really interesting thing is that NSA was actually better than standard attention on a lot of those tasks, even though it's being more selective with its attention.
So it's more efficient, A&D, more accurate?
That's right. It might seem counterintuitive, but there's a reason for it. Remember how NSA learns to be sparse during training?
Right.
Well, that forces it to focus on the most important information and to filter out all the noise that might distract other models.
It's like training your brain to ignore distractions.
Exactly. And that focus seems to lead to a deeper understanding of the text and ultimately better performance.
That's amazing.
And where NSA really excels is in tasks with really long texts, like, analyzing an entire code base or understanding a dense scientific paper.
Right. Those are the scenarios where standard attention really struggles.
Exactly. And in those cases, NSA consistently outperformed other methods. It even achieved perfect accuracy in this needle in a haystack test, showing that it can find those crucial pieces of information buried in tons of text.
Okay, that's impressive. But what about tasks that require more than just finding information? Can NSA handle that kind of logical thinking needed for complex reasoning?
That's a great question, and that's something they looked at very closely. They specifically tested NSA on its ability to do this thing called chain of thought reasoning.
Chain of thought reasoning.
Yeah, it's a way of solving problems by breaking them down into a series of logical steps, like how you might solve a math problem, working through each equation step by step.
Gotcha. So it's not just about finding the answer, it's about understanding the steps to get there.
Exactly. And to test this, they trained both a standard attention model and an NSA model on a bunch of math problems. Then they gave both models this really challenging math competition problem to solve.
Okay, how do they do?
Well, NSA consistently outperformed the standard model. It showed that it could not only handle these long contexts, but that it could also reason logically within those contexts.
So it's efficient, it's accurate, AD, it's a logical thinker.
Yeah, it's shaping up to be a really promising approach. Of course, there's always more research to be done. But one question that comes to mind is, how does all this translate into real-world efficiency gains? I mean, the whole point of this sparse attention is to make these models less computationally expensive.
Right. What good is all this performance if it needs a supercomputer to run.
Exactly. And the researchers actually looked at that very closely. They analyzed NSA's efficiency during both training and inference.
Okay, let's break that down. First, how did it perform during training?
Well, they compared NSA to a standard attention model, and they used this highly optimized software library for AI. And the results were really interesting. NSA was significantly faster, especially as the text length grew.
The longer the text, the bigger the advantage.
Exactly. At the longest lengths they tested, NSA was something like 9 times faster than standard attention during training.
Wow, that's huge. What about inference? When the model's actually processing new text.
Well, inference is a little trickier. It's often more about memory access than raw computational power.
So it's how quickly the model can get to the information it needs.
Exactly. And this is where NSA's design really pays off, because it only needs to access a small part of the total information. It avoids that memory bottleneck.
So it's not just reducing the computations, it's being smart about how it accesses information.
Precisely. And in their tests, NSA was up to 11 times faster than standard attention during inference.
So big improvements in both training and inference.
Yeah. And it opens up a lot of exciting possibilities for the future. Imagine models that can analyze entire code bases, or understand scientific papers in depth, or generate really epic stories, and all while running efficiently on regular hardware.
It sounds like NSA could really be a game changer.
It definitely has the potential. It shows how powerful it can be when you combine these innovative algorithms with a deep understanding of the hardware and the structure of language.
This has been a fantastic deep dive. We've gone from the limitations of standard attention to the intricacies of NSA's design, and we've seen its remarkable performance. But before we wrap up, are there any broader implications or open questions we should think about?
Yeah, that's a great point. I think the biggest takeaway here is that AI is constantly changing. New approaches are being developed all the time, and those approaches are leading to some pretty amazing breakthroughs.
So if NSA is this good, where do we go from here? What are the big exciting applications that this could unlock?
Well, the possibilities are really huge. One area that could see some major change is scientific discovery. Imagine language models that can go through all those scientific papers and research and find connections between different discoveries, maybe even come up with new hypotheses for experiments.
That's amazing. It's like having an AI research assistant working with the scientists.
Exactly. And it's not just about analyzing the research that's already out there. These models could actually help design new experiments, optimize those research workflows, and even speed up the whole process of discovery.
It sounds like a whole scientific revolution powered by AI.
Yeah, I think we're on the verge of something really big. And it's not limited to science either. Think about software development. NSA could let us build models that analyze entire code bases, find those hidden bugs and security vulnerabilities, maybe even suggest improvements.
Code. Developers are working with these AI tools.
Exactly. It would free up developers to focus on the more creative parts of design and let the machines handle those tedious and error-prone tasks.
And what about creative fields? Could NSA change how we write stories or compose music or create art?
Absolutely. Imagine writers working with language models that can understand and create really complex narratives. Or musicians collaborating with AI that can compose entire symphonies.
That's incredible. The possibilities are endless.
Yeah, we're really just starting to explore what this technology can do.
It sounds like NSA could completely change how we work, how we create, even how we think.
Yeah, I think it has that potential. But like with any really powerful technology, we have to make sure we use it responsibly.
That's a great point. What are some of the things we need to consider as we move forward?
Well, one really important aspect is fairness and bias. We need to make sure these models aren't perpetuating existing societal biases or creating new ones.
So it's not just about the technology itself, it's about the values that we embed in it.
Exactly. We also need to think about transparency and accountability. How can we make sure these models are making decisions in a way that we understand and can audit?
That's a tough one.
It is. But it's something we have to figure out. If we want these technologies to benefit everyone, we need to make sure they're developed and used ethically.
I think that's a great place to end. This deep dive into natively trainable sparse attention has been a real eye-opener. We talked about the limitations of traditional language models, and then we went deep into how NSA works and how well it performs.
Yeah, it's been a fascinating discussion.
Absolutely. And I think it's really just the beginning for NSA. It'll be exciting to see where it goes from here.
Yeah, the future of AI is full of potential.
Yeah.
And if we develop it responsibly and use it thoughtfully, we can really make a difference in the world.
Well said. Thanks for joining us on this deep dive. We hope you'll tune in again for our next exploration of cutting-edge AI. Until then, keep learning, keep questioning, and keep pushing the boundaries of what's possible.